Diagonalization. This part is from section 5.3. It can be considered as application of eigenvalue and eigenvectors. So we learned how to find eigenpairs and corresponding eigenspaces. So using that knowledge, we can do diagonalization of so-called PDP inverse. So let's first look at the definition, what we mean by diagonalization. So for that purpose, we need to introduce what we mean by similar. So M by M matrix A is similar to M by M matrix B. A is similar to B, usually denoted by A with wave B. If there exists an invertible matrix P such that A equals P times B P inverse. And this similarity of two matrices can be used for simplification of some computations. For example, if you have a to the kth power, then a to the kth power can be written as a times a times a times all the way times p b p inverse. Each one is a. So we need to multiply a k times. This is a huge computation if k is big, but we can see that if we have like diagonalization, then we can have p inverse and p cancel each other. These two cancel each other, and p inverse and the p right after this cancel each other, and this p will be cancelled with p inverse before this. So at the end, we can have p and b, there b to the kth power, and the last one is p inverse. In other words, a to the kth power is also similar to b to the kth power. And if b is diagonal, for example, b is given by b1, b2, b3, and other things are just 0, then b to the kth power is basically multiplication power of each diagonal entries, and other things just remain 0. So b to the k is very easy to be computed if b is given by diagonal. So this is why we want to have diagonalization of matrix. So maybe we should add one more definition. By diagonalization of a given matrix A, M by M matrix, we want to find two matrices. One is diagonal matrix, and second one is invertible matrix, P. Such that A can be written as P times D times P inverse. Alright, here's one example. Suppose A is given as 2 by 2 matrix. Then usual question is, can you diagonalize this A? In other words, can you find two matrices P and D such that A satisfies P, D, P inverse? Now this is the ultimate question, but to understand the concept, we give P and D two matrices. You can verify A and A can be diagonalized. In other words, A equals P D P inverse. This is the checking procedure is nothing but computation, so we are going to skip that. And the application of or advantage of this diagonalization is, suppose you have A to the k's power. Suppose you are interested in, for example, A to the third power. Directly computing multiply A by itself 3 times, you can get A to the third power. Instead, if you have diagonalization, this representation, what you can do is P d third power P inverse. In other words, this gives you d 5 to the third power, 3 to the third power, 0, 0, and P inverse. You can, maybe it's not really convincing if you're just looking at 3, how it simplifies the computation. But if you have 30, then the only thing is you change 3 to 30 and this 3 to 30. And this is much easier. You have 3 multiplications. But if you do multiplication of A by itself 30 times, it is a long procedure, long computation. So this is diagonalization. For n by n matrix A is called diagonalizable if A is similar to diagonal matrix. And A is diagonalizable if and only if A has n linearly independent eigenvectors. We are not going to discuss this more details, but we want to know what we mean by diagonalizable. In other words, if A is similar to some diagonal matrix, so you can write A equals PDP inverse, then this is diagonalizable. And if A has n distinct eigenvalues, then it is also diagonalizable. So the next question is, given a matrix, how do you find P and D to diagonalize A? So to do that, you can multiply P both sides on right hand side. So if you multiply P here, and then you need to multiply P on the other side, and then P inverse P can be cancelled. So in other words, this means AP equals PD. If you write P as first column, second column, nth column as symbolically, so P1 to Pn, and diagonalization D means a matrix of lambda 1, lambda 2, lambda n, and everything else are 0, then we can instantly write this thing in terms of P1, Pn, and lambda 1, lambda n as AP1, APn, lambda 1, P1, lambda 2, P2, and all the way like this. So that means first column match first column. In other words, AP1 equals lambda 1, P1. So if you write AP1 equals lambda 1, P1, it can be interpreted as lambda 1 is an eigenvalue of A, and P1 is corresponding eigenvector. And the same thing for lambda n. So every lambdas must be, so those diagonal entries must be filled up with eigenvalues. And this P must be filled up with the columns given by eigenvectors. So each column will be eigenvectors. Now, we're going to conclude that how to find P and D to diagonalize A. So to do that, first you want to find spectrum of all the eigenvalues of A, lambda 1, lambda 2, lambda n. Sometimes you want to make it, write it from the largest to smallest, and find corresponding linearly independent eigenvectors for each lambda. So for lambda 1, maybe you can find P1, lambda n, you can find Pn. So you have n many vectors, column vectors. Now P is just packing them together, all eigenvectors, to a matrix. D is put those eigenvalues in a diagonal entries like this. So this is D. So as long as you know how to compute the eigenvalues and corresponding eigenvectors, then finding P and D is just rewritten everything into a matrix, two matrices. Let's look at one example, 2 by 2 matrix. So 7, 2, negative 4, 1. And we want to diagonalize that. So this is A. By diagonalizing means we want to find some matrix P and D and P inverse. So you really want to find these two matrices. So how do you do that? First, I want to find eigenvectors, eigenvalues, or spectrum, which means by solving determinant A minus lambda I equals 0. So what is A minus lambda I? A minus lambda I is you first copy A first, and for each diagonal entries you need to take away lambda, so subtract lambda, and then determinant equals. This is what you want to solve. So 2 by 2 matrix, we want to do multiplication and take a minus. So in the end, you come up with quadratic function plus 7 plus 8, which is 15. Now for quadratic equation, we can do factorization. So I write first larger one, second smaller eigenvalues. So I have two eigenvalues. Now for each eigenvalues, I want to find at least one eigenvector. So so that actually gives me two substeps. For lambda 1 equals 5, what will I do is I want to solve A minus lambda I and 0 homogeneous equation. Or that means A minus lambda I x equals 0. So you want to find this, or augmented matrix. So A minus lambda I, here we already have this here. So what you do is just copy, but when you copy, you want to replace lambda by 5. So the augmented matrix is going to be 7 minus lambda and 2, negative 4, and 1 minus lambda, 1 minus 5, which is negative 4. And this is not closing the matrix, so we want to write 0, 0 here. And obviously, after a few rows, you're coming up with just one row, one useful rows, and this is basic variable, this is free variable, because you have staircase and with the pivot at the beginning. So this is x1 plus x2 equals 0. That means I can write this x1 equals negative x2. x2 is free variable. So the PBF is x equals x2 negative 1, 1. So that gives me P1. Okay, so this is eigenvalue corresponding to 5. Now, second, I want to move on for lambda 2 equals 3 and solve A minus 3I zero. augmented matrix. A minus 3i, if you go back there, so it is A minus 3 lambda I. So we replace lambda by 3. So 7 minus 3 is 4. So 4, 2. Here's negative 4, negative 2. So 4, 2, and so that is 4, 2, negative 4, negative 2. Of course, we can do this as 1, 1 half, 0, 0. I forgot to put 0, 0 here, so 0, 0. Then if we solve that, x1 from first line, we can have x1 equals negative 1 half x2. x2 is x2. So PBF is going to be x2 negative 1 half 1. So this gives me P2. All right, now the last step is just put them together. So we have information for lambda 1. So I want to, so this is for lambda 1, which is given by 7 or 5. Lambda 2 is given by 3, and for lambda 2 we have negative 1 half 1 for lambda 2 equals 3. So negative 1 half 1, which is, so this is P2. So P is going to be P1, P2, negative 1, 1, negative 1 half 1. And D is going to be 5, 3, 0, 0. And P inverse is just as usual. You want to find its P inverse from P. Usually to find the P inverse, we want to do this. So you want to do PI, and after some EROs you can come up with P inverse, and second half will be P inverse. There's one remark. If you're not really want to have fraction in your answer, you can multiply 2 for both entries, because any vector multiplied by a scalar, it is still eigenvector. There's one more problem. I'm just giving this leave it as exercise. If you need help for this, you may come to my office hour, and the answer suppose be, so if you solve that, you can come up with lambda 1 equals 1, but lambda 2 and lambda 3 both are negative 2. So from here we can have P1 equals negative 1, 1, negative 1. And from here you can find P2 as negative 1, 1, 0, and P3 is negative 1, 0, 1. So for P, you can arrange them as a matrix, putting every eigenvectors together. So this is from P1, P2, P3. And D is going to be lambda 1, lambda 2, lambda 3. 0, 0, 0, 0, 0, 0. All right. Thank you.